Okay, geometry 3.1 is the start of three sections right here that some people really like in geometry and some people really dislike. For better or worse, these three sections we're going to do aren't really going to feel like math to you guys. There's not a whole lot of numbers involved. We're not solving any equations. We're not even really dealing with geometric figures. What we're dealing with in these three sections is the introduction of logic as a subject that we try to teach within the geometry course. So these three sections, 3.1, 3.2, and 3.3, are all going to feel a little bit weird, but let's get a little vocab down and see if we can figure out what it is that we're trying to learn here and how that's going to relate eventually back into math and into geometry. So the title of section 3.1 is Conjectures and Counterexamples. Might be two words you're not familiar with, so let's dive into the first one right here. A conjecture, vocab word that should have been underlined there, is an educated guess that can be tested. And if that definition sounds familiar, it's very similar to the definition of a word you should know from your science classes, which would be hypothesis. Just like a hypothesis, a conjecture has to be an educated guess. It's not just something random that you just say, oh yeah, this is going to happen. There's got to be some reason why you might think that, but the important thing is what comes at the end of this definition, that a conjecture can be tested to determine whether it is true or false. And obviously in math, we're much more interested in true conjectures than we are in false ones, but that's the definition of what that word means. So when we see it in action in a mathematical context, let's take a look at these types of problems where we're being asked to write a conjecture that describes each pattern and then find the next three terms in each sequence. So when I said these sections weren't going to be overly mathematical, well, here's one where there are numbers involved. So most of what we do in math, guys, at one level or another is some type of pattern recognition, and that's kind of what we have going on right here. So as we look at example A, we're looking at some four-digit numbers here, 1,996, 2,000, 2004, 2008, and so we're supposed to write the conjecture that describes what is happening. Probably the easiest relationship to see when you're given a series of numbers here, I should say a sequence of numbers, is an addition pattern, and that's what's going on right here, guys. As we can see, we're just adding 4 to get from 1996 to 2000, and that same idea of adding 4 works to get us to 2004 and 2008. And so our conjecture right here, I would just say, is that simply that we are adding 4 each step along the way. That would be my conjecture. And now filling in the next three terms in the sequence, I would just keep adding 4 to 2008, which would get us 2012, plus another 4 would be 2016, and another 4 would get us to 2020. And that's what's going on with example A. Now, you might ask yourself, what's special about those numbers right here? Right there, probably three things. Number one, all 4 of those there are presidential election years, everybody. 1996, all the way on up to 2020, and now it's 2024, and that one would be the next term in that sequence. There are also years in which we have Summer Olympic Games and also leap years. Each of those years that's listed there, we add that extra day in February for the 29th. Okay, let's move on to example B. This one's maybe a little bit tougher to see. We're going from -6 to +12 to -24 to +48. Now, a weird thing to notice about B is that the signs of your numbers are alternating. Negative, positive, negative, positive. And what that tells us is this is not an addition pattern the way the last one was. Just to prove that, to get from -6 to 12, we would have to add 18 to do that. If we were to add 18 here again to 12, that would get us +30. But there's no way it can go back to a negative number once it's turned positive if we're just adding the same number over and over and over again. So B is not an addition pattern. What we might want to look for instead then is a multiplication pattern. How would we get from -6 to +12? We could multiply that by -2. The negative would change the sign, and doubling the 6 would get us 12. And now ask yourself, does that same idea, that same strategy of multiplying by -2 get us from 12 to -24? Yeah, it does. And that would also get you from -24 to +48. So what looks like is happening here in B is that we are multiplying, here we go, by -2. That seems to be our conjecture. So grab your calculator here if you need it, guys, as I would guess that you do. 48 times -2 is going to get us a -96. -96 times 2 is going to be a positive 192, and then a positive 192 times -2 is going to get us a negative 384. I want to show you guys a quick trick here on the calculator I have on my iPad. Your calculators aren't obviously going to look like this, but they are going to do kind of the same trick right here. So let me show you what I'm talking about here, guys. The first term in that sequence was -6. So I'm going to do this on my calculator. I'm going to type in -6, not hit anything at all, and just hit enter. And not surprisingly, it gave me the answer -6. Now, if I just hit the times button, everybody, the multiplication key, you'll see that a little ANS pops up, which means last answer. So I wanted to take that last answer times -2, and there's the 12 that I was looking for. Now here's the fun part, guys. If we just hit enter here, it keeps doing that same process over and over again, but each time you do it, the last answer gets replaced by the previous answer. So when I just hit enter there, you'll notice that I ended up with a, let's see, a 12 right there, and it's because that 12 was the previous answer right there. So all you have to do here, guys, this is kind of fun, is just keep hitting. Let me get my cursor back where it should be. There you go. Enter, enter, enter. And if you just kind of keep doing that over and over again, you'll get the next answers there pretty quickly. And there's the -384 that I wanted to end on. Okay, so A was an addition pattern, B was a multiplication pattern, C is a little bit weird. And if we were in class, this is one I would let you guys just kind of stare at for a minute, chew on it, and see if you can make any sense out of it. So you might want to pause the video right now, just take a look at C and see if you can figure out what's happening. Okay, so as we look at C, the question probably on your mind should be, how do we get from 0 to 1? Well, that one seems obvious in terms of addition. You would add 1. But then how do you get from 1 to 1? That's a little strange. We're adding 0. All right, and eventually here we're going to be adding 2, and eventually here we're going to be adding 3. I guess I should have done all this. That's a +1. That's another +1. This does not look like a simple repeated addition pattern like we had up here in example A. And it's not a multiplication pattern either, because there's no way to get from 0 to 1 using multiplication. The key to this pattern, guys, this is something famous in mathematics, I'll tell you the name of it in a second, is that the first two terms have to be given to you. And then if you add those two terms together, that gets you the third term. 0 plus 1 is going to get you 1. And now if I just slide this over a little bit, the second term plus the third term, 1 plus 1, gets you the fourth term, which is 2. Same thing happens here. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. Okay, so what's happening here, my conjecture would be, ooh, this is a little bit of a pain to write, but I would say each term is the sum of the previous two terms, okay, of the previous two terms. All right, so we would add the 5 and the 8 together to get 13 for our next term. Then we're going to have to add, I wish my box was a little bigger, the 8 and the 13 together, and that's going to get us 21. And then we'd add, that's not what I wanted, the 13 and the 21 together, and that's going to get us 34 for the, what, 7, 8, 9, 10th term right there. All right. C, everybody, is a famous sequence in mathematics here called the Fibonacci sequence, and I meant to look up how to spell this. I think it's only one B, Fibonacci, and then two C's. All right, the Fibonacci sequence, kind of famous because it actually occurs in nature, not with these exact numbers, guys, but for example, one of the places it occurs is in a sunflower. All the little rings around the center of the sunflower that have seeds in them, they follow this pattern now, that the number of seeds in the next ring is going to be equal to the sum of the previous two. Or so I've read. I've never actually counted it, got to be honest with you guys. Okay, so that's pattern recognition, and that's writing conjectures and using it to complete a sequence. Okay, with that in mind, let's take a look at what we might be asked to do here in terms of making a conjecture about some things that are a little bit more abstract than what it was we were just dealing with. The sum of two odd integers. That's what we're asked to deal with here in example A. So what I would tell you guys to do here and this would be more interesting if we were in a full class with 20 or 30 people there, I'd ask everybody on their paper to write down two odd integers and then see what happens when you take the sum of those two numbers. So let me just write down a few examples. 5 is an odd integer, and if I added that to 7, which is another odd integer, I get 12. Okay, that doesn't mean anything to me. Let me try another odd integer. How about 21 plus 9? Both odd integers, I'll add those together, and I'll get 30. Remember, guys, integers can be negative. So what if I took something like negative 11 and I added, what have I not used yet? How about 13 to that? I end up with 2. How about negative 37 plus a negative 15? Just trying to come up with a lot of different things going on right here. That ends up equaling a negative 52. Now, there are an infinite number of examples we could come up with. Now, we've just done 4, but what I want you guys to do is take a look at the 4 results that we came up with here and ask yourself, do those 4 answers have anything in common? What I'm hoping you noticed is that every time we add two odd integers together, we end up with an even integer. Okay, so that is what I would say for our conjecture right here. The sum of two odd integers, I should say, is an even integer. Just kind of make a complete sentence out of that right there. And that's going to be true no matter which two odd integers you pick, everybody. B is a little bit weird. How about the product of 4 and any integer and then minus 3? So let's try it. Product means multiplication. So 4 times an integer of, let me go with 7, and then we're going to go minus 3 and see what happens. We have to do multiplication first. So 4 times 7 is 28. 28 minus 3, 25. That doesn't tell me much. Let's try some other things. How about 4 times, let's go big, 21. That is an integer. Actually, 4 instead of any integer, let's do an even one this time. How about 4 times 22 minus 3? Okay, 4 times 22 is going to get us 88. 88 minus 3, 85. How about 4 times an integer like 0? We forget about that, but 0 is an integer as well. Minus 3. 4 times 0 is 0. Minus 3 is negative 3. So 3 is probably good, guys. Let's take a look. What do we notice about all 3 of our answers here? Looks like they are all going to be an odd integer. So that's what I'll say right here, is an odd integer. And there's our conjecture there about what's going on in part B. And then C, we actually get a little bit geometric here for the first time in a while. They want us to make a conjecture about the length of line segment AB and line segment AC if B is the midpoint of segment AC. Well, we've seen enough problems like this so far this year, I hope, to know that the tricky thing about a problem like this is that it's all text, and it's hard to figure out exactly what's going on if we don't have a diagram. So let's draw one. We're talking about the lengths of two line segments, AB and AC, if B is the midpoint of AC. So what I think I need to do, guys, is start with a line segment right here and say we're dealing with a midpoint. So I'm going to put a dot right there in the middle. Now I'm reading the second part of this sentence now after the comma. B is the midpoint of AC. So I'm going to put B right there in the middle, A on the left, C on the right. To show that it is a midpoint, I'm going to put tick marks here on AB and BC. So they want us to come up with a conjecture here about the length of AB and BC. So pick a number, guys. You can let AB be any measurement you want as long as it's positive. So I'm going to go ahead and put 8 here. I'm just choosing a random number for the length of AB. But guys, that's the last choice we get to make now. BC has to be the same length as AB because B is the midpoint. So that means that BC would have to be 8 as well. And they want us to make a conjecture about the length of AB and AC. So AC is the whole segment right here, and it would have a length of 8 plus 8, 16 for the measure of AC. So what I see here, guys, is that the measure of AB is 8, and the measure of AC is 16. And what's special about those two numbers? 16 is the sum of 8 and itself. Or better yet, I think we could say this, that whatever the length of AB is, we'd have to multiply that by 2 to get the length of AC. So AC is equal to 2 times the measure of AB. That would be the conjecture I would make about this, and that would be true even if we had chosen a totally different number here other than 8. Like, for example, if I put an 11 right here, well, this becomes 11 and this becomes 22, and sure enough, 22 is equal to 2 times 11. So that's still going to be the case. All right, so those last two slides deal with different types of setups right there, but in each case we were asked to make a conjecture about the information that was given to us. There we go. All right, let's take a look at what's going on this fourth slide. Now we're going to introduce the word counterexample. So counter kind of means something that goes against the way you think it's going to go. And of course, we know what an example is. So a counterexample is something, and I probably should have said a statement. That's a little fancier than something, but okay. A statement that disproves a conjecture. Now, whoa, whoa, whoa. Proves means shows something is true. Disproves then means shows that something is false. If you remember all the way back on the first slide, we defined a conjecture as an educated guess that can be tested, and we did not say that a conjecture had to be true. So, a counterexample is something you can use to disprove a conjecture. And here's how it works. You have to satisfy the first part of the conjecture, but then you have to contradict the second part. Contradict means going against something. So, that definition is a little bit wordy right there, but I think once you guys see it in action, you'll realize this isn't all that bad. Let's take a look here, guys. We are going to provide a counterexample for each conjecture. Now, right there, the directions are already telling you something. You couldn't provide a counterexample for a conjecture if it were true. By them asking us for a counterexample, they're telling you right now that each of these statements is false. Now, here's the big kicker, guys. For a statement in mathematics to be true, it has to be true all the time, 100%. And if you can even find one case where it's not true, then we would have to say that that statement is false. Okay, overall. To be true, it has to be always true. So let's take a look at statement A here, guys. If it is fall, then it is October. Now that statement right there, if you just look at it very, very quickly, you might be inclined to say, oh yeah, that's correct. In fact, as I'm making this video right now, you can see in the top left corner of my screen, it is Wednesday, October 16th right now, and sure enough, it is fall outside. But what we're trying to do is determine whether or not this statement is always true. So let's look for a counterexample, and let's go back to this. A counterexample is something that disproves a conjecture by satisfying the first part but contradicting the second part of your conjecture. So what I'm looking for, guys, in this case, I'm looking for a day, or better yet, a date. I'm looking for a date that is in the season of fall but is not in October. I want this thing to verify the first part but then contradict the second. So my counterexample, and I usually just use CE as an abbreviation for counterexample, could be any date that would be fall but not October. So I'm going to go with Thanksgiving, everybody. I'm just going to write down November, and I believe Thanksgiving is the 28th this year. This is a counterexample that shows you that this statement is not 100% true, because November 28th is a date that is in the fall. So yeah, it verifies this, but it's not in October, it's in November instead, so it contradicts the second part. Now, just finding that one counterexample tells us that statement A is not always true. And in a simple binary choice here, guys, if we had to say if a statement was either true or false, to be true, it has to be true all the time. Finding one counterexample tells you then that this statement right here was false. Now, in the realm of some other types of questions, there's something called, you guys all understand what true-false means. That's kind of what I was just talking about. In the realm of ASN, always, sometimes, or never true, this statement right here would be a sometimes. There are days that are in the fall where it is also October. Again, like today, October 16th, but not always. So we're going to ignore that right here for now, and there's our counterexample. How about the second statement right here? If an animal is a bird, then it can fly. If I were to ask that as a question to a small child, maybe somebody who's 3 or 4 years old, kids might very well tell you that that statement is true, because it is true that most birds can fly. You might even say that's one of the defining characteristics of a bird. And when you were 3 or 4 years old, that's probably the way you looked at things. But for this statement to be true, it needs to be true 100% of the time. So the question becomes, can we find a counterexample? A counterexample would need to be something that is a bird but cannot fly. So a common counterexample people will give me there, a bird that cannot fly, would be something like a penguin. All right. While we're at it, there are others. A turkey is a bird that cannot fly. An emu, everybody, which is kind of like an ostrich, lives down in Australia. Those would all be examples as well, and I'm sure there are more, but that's pretty good for now. You really only need one, guys. So you need something that is a bird but cannot fly, and any of these three works as a counterexample. So once again, then, we could conclude that this statement right here is false because we were able to find a valid counterexample. Okay, guys, that's everything we got for you right here in 3.1. It's not a real long section, and most of your homework right here is going to ask you to use these ideas that we just talked about in this video here to come up with conjectures in many cases, and then also to come up with counterexamples to prove that a conjecture, even one that might seem to be true at first, often is not. Okay, that's a wrap on notes. Good luck on the homework, everybody.